because this is kind of, it's a really different flavor from any of the other ones that we've done, where we're kind of posed an abstract problem. There's not really an application in mind. We just want to know what is the difference between maximum and minimum of the quantity a squared b squared over 72, where a and b are two non-negative numbers, such that a and b are equal to a plus b is 6. So we need to maximum and minimum of that quantity right there. That's my omega. My objective is to find the maximum and minimum values of that function and take the difference of them. And there's a constraint on me here that a plus b is 6. And furthermore, there is a domain restriction in terms of a and b are two non-negative numbers. So a and b are two non-negative numbers means that a comma b is bigger than or equal to 0. So we're not going to consider what negative values for those two things. And as usual, we're going to use our constraint as a way to eliminate a variable from our objective function. So our objective function omega was just given to us. Didn't need to draw a picture in order to figure out what it was. We just got it for free. And I need to eliminate a variable because I have too many variables. And I'm going to choose to eliminate b because I want to work with the one that's more alphabetically first, just because. So I'm going to solve a plus b equals 6 for b and substitute. So I have b equals 6 minus a. And then if I put that into my objective function omega, I have a squared times 6 minus a quantity squared over 72. And now I have my single variable objective function. Very nice. Now I can do my optimization. This is a 4th degree polynomial. And so all of the critical points will come from derivative 0 conditions. So we want to solve omega prime equals 0. The question is, do I want to distribute out first? I think I might just use the product rule and the chain rule. So I'm going to go 1 over 72. That way I don't have to deal with that constant when I do the product rule. And I'll have 2a times 6 minus a squared plus a squared times 2 times 6 minus a times negative 1. That negative 1 came from the derivative of the inside when I used the chain rule to chain out the derivative of the inside. Now I'm going to multiply by 72 on both sides to clear out that leading factor. I don't want to deal with that. And then I'll just do some rewriting down here, and I'll have 0 equals 2a times 6 minus a squared plus, minus, because I have a minus sign, minus 2 times a squared times 6 minus a. And it might be tempting to start factoring, distributing things out, but I'm not going to distribute things out. I think I'm going to factor. So I'm going to factor out a common factor of a, and I'm going to factor out a common factor of 6 minus a. So I'll have, and I'm going to divide by 2 on both sides to get rid of my 2's. So I don't have to deal with those anymore. So I'm going to have 6 minus a is the leftovers after having factored out an a and one of the 6 minus a's. And in the other term, I have minus a, and then that's times a times 6 minus a. So that was me factoring out a common factor of a from both. I have a leftover on the second term, and I factored out a 6 minus a from both, and I have a leftover factor of 6 minus a. So these are the leftovers, and then these are the two things that I factored out. And that's still equal to 0. Okay, so now I have the product of 3 things equals 0, which tells me that either a equals 0, or 6 minus a equals 0, or 6 minus 2a equals 0. So those are my 3 critical points. A equals 0, a equals 6, and a equals 3. So now we got to use those critical points, and I want to find the values of b. I'm going to find the values of b by using my constraint equation that I solved for b, and I can just take my values of a and plug them in to that expression to generate the corresponding value of b. So I get 6, 3, or 0. So I am now going to take and build a table of my crit points and my omega values to figure out which ones are the biggest. I have 0, 6, 3, 3, and 6, 0. I'm just going to take those points and feed them through my objective function. And I'll have 0 and 0 on the outside. And on the inside, I will have 9 times 9 over 72 is 81 over 72. So my minimum value is 0, and my maximum value is 81 over 72. Why do I care about that? I want to find the difference between the maximum and minimum value of the quantity. It's guaranteed to be positive. And so the difference is 81 over 72 minus 0 equals 81 over 72. I can't consider any smaller value of a than 0 because then it would be negative, and I can't consider any bigger value of a than 6 because then b would be negative. So I know that my values of a and b here are all of the critical points in everything that I want to study. So the answer is 81 over 72 for this problem. I consider this on the easier side. The thing that makes this one more complicated is that we have to compute both the min and the max and then take the difference of them. But, like if we just wanted to maximize that function, it's pretty easy. The hardest part, I guess, was the factoring down here. Why don't I just create a table for all possibilities that add to 6? Oh, because there's an infinite number of them, because we're not just considering integers. We have to consider every single number inside of the interval from 0 to 6, right? Like a is an element of the interval from 0 to 6, which includes numbers like 0.1 through 0.5, the number pi, the number e. So there's an uncountably infinite number of values I have to consider, because we're not just doing integers, we're doing every possible value. These problems, they keep giving you numbers where things work out nicely and you get integers because they're training problems. Out in the real world, the actual likelihood of getting integers for these things is probably 0.